All right, so in this lecture, we are going to continue our discussion from the introduction to the neural network. And so far we've seen what is a neural network and what are the basic sort of, constituents of a neuron. We saw some activation functions, and then we also discussed, how do you actually tune the weights of a neural network using an algorithm called backpropagation, which really relies on the chain rule from calculus. And then we saw some specific examples of how the error at the output neuron or the output layer of the network can be propagated back all the way to any of the weights, and the weights are adjusted to minimize the error for some data set. So today we will start looking at convolutional neural networks, which are, if you recall our discussion from self-driving cars, a lot of these perception tasks involve looking at or detecting where a vehicle or a pedestrian or objects are in a given image or a sequence of images, which is a video. And so today we will build the intuition for how that works, and the key to getting that to work is understanding a different kind of neural network called convolution neural network. So before we get started, I just want to acknowledge the people who have made many of these slides that I'm using in order for this lecture. So I just want to make sure that their work is also acknowledged. All right. So let's get started. We'll start with a toy example, just like before. And here our goal is that we are given an image. So it could be let's say a bitmap image to keep things simple, which in other words is that a pixel can only be white or black. And let's stick to our previous convention where a white pixel has a value of +1 and a black pixel has the value of -1. So we are given this 2D image, which is essentially a matrix of pixels. And the job of this convolution neural network is to classify whether the pattern present in this image is that of a cross or a circle. Right? So it's similar to the classification task that we already looked at in the previous lecture, where we wanted to classify whether the pattern was, solid or vertical or diagonal or horizontal. So here our pattern is, a little bit more complicated than that simple example. By the way, the example that we've already studied before, or the way to construct this fully connected neural network that we've studied before, can also be used for this problem. You don't need convolution. So you can, I haven't counted the pixels on the slide yet, but it looks like it's like 7 by 7. So you can have, all the pixels as the input layer of the neuron. So you flatten this out with the same trick as before, and you can have a fully connected neural network, tune the weights to predict whether that's a cross or a zero. The problem is that not all crosses look similar. Right? On the left-hand side is like the ideal cross pattern that you can expect in this image. But the image on the right-hand side, a human would also classify that as a cross. Whereas it doesn't really, it's not as let's say similar or as straightforward a cross as one would expect. So if you did in fact train a fully connected neural network to solve this problem, it would struggle because of the variability in the spatial distribution of what this cross or a zero or a circle looks like. Right, so these crosses can be smaller or larger, so there's a variation in scale. They could be thinner or thicker. They could be rotated or some twisted sort of a cross, which is kind of what the image on right-hand side is. It could be a non-symmetrical cross where not all the arms of the cross are also the same. So we want to not think anymore in terms of individual pixels, but instead the intuition behind convolution is the following, that let's think about what a cross is actually made up of. We can actually think that and is also shown in this slide, that you can think of these small images shown in the green, purple, and orange sort of small subsampled images. You can think of that a cross is actually composed of these canonical images or features. Right? And these features can be arranged in more than a single manner, and the resulting image could still look like a cross. And so it's these features which are common to all crosses. That's the assertion or the hypothesis. And so as long as we can find whether these features exist in our image or not, we can decompose the problem of finding a cross to finding overlap with some features and the original image. So this will become more clear when we look at an example. So based on this image, it's reasonable to see and say that a cross image in our toy problem is composed of these three features. And so these features are nothing but smaller images, right? So our original image was 7 by 7, and these features are 3 by 3. For now, I have very conveniently just shown you what these features are without having answered or dealt with the problem of where these features are coming from. So we will address that question in a little bit later in this lecture. But for now, the intuition that I want you to take away is that given these features, you can imagine taking this feature and kind of matching it with the part of the image that corresponds to the same sub-image as the feature itself. So here are some examples. This sort of backward diagonal, which is shown in the top left, it matches with this part of the image right here. And so we have more matches in other parts of the images. And so these three features are enough to describe what a cross looks like. So while the intuition now is that we are advocating that given some features, we would want to find where in our original image do those features appear. Or we may not always have an exact match, but do we have some sub-images in our original image which overlap or are very similar to our feature set? Just notationally, these features are sometimes also called filters of a neural network or a convolution neural network. And then you will also hear this term kernel of a CNN. They're all referring to these features, the smaller images. So what is the mathematics now behind finding whether this feature appears or something close to this feature appears in my original image? And that math which tells us whether there's a good overlap or this where in my image can I find this sub-image or this filter, appropriately that math is called filtering. And so filtering is the idea that I'm going to take a filter or a given sub-image or a feature shown on the top left in this slide, and I'm going to slide that feature throughout my image. And as I am sliding it on my image, I'm going to do some mathematical calculations, the output of which will be an indication of whether or not in that instance or in that part of the image, is that similar to my feature? And that is what is called filtering. And in other words, it's also filtering is one of the steps of convolution. So let's look at sort of a summary of what filtering is. First, we take the feature and we overlay or line it up with the image. And then we multiply each pixel value of our feature with the corresponding pixel value in the overlap of the image. So this is sort of like a pixel-wise multiplication. So in a 3 by 3 filter shown here, you will multiply each pixel of this 3 by 3 filter with the corresponding value of the overlap in our image. And so you will get some output as a result of this multiplication. And so what filtering does is we sum up all the output values in that resulting image, and then in this case, in this example, we divide that value by the total numbers in the feature itself. So once again, let's look at an example that will make it very clear. So we have this same feature vector on the top left, and in an example, I am just showing you that you would ideally begin overlapping from the, let's say, the very top left, right? So sort of starting with the top left pixel here. But at some point during the sliding, you will encounter an instance which is shown here. And so what the element-wise multiplication is referring to is what I'm trying to indicate here is that you take the product of the value of the pixel in your filter with the corresponding value of the pixel in your overlap portion of the image. So in this case, it's a mere 1 multiplied by 1, so the output is 1. And then you repeat that for all the values in my filter. And so here's the output of that process. So you will do that, and the resulting sort of output of this filtering is shown here. And this is not, we are not yet done. This is merely the result of multiplying every pixel with the corresponding pixel in my filter. So once we have this output, what was indicated in the sort of the sequence of steps to be followed is you sum up all the pixels in this output. So very conveniently, the output in this case is all ones. So we sum it up and we divide it by the number of pixels. And whatever is the result, which is 1 in this case, we store that as the outcome of the filtering process between my feature or my filter and a part of my original image. So what have we really done? Why are we doing this? Let's try to think about the intuition behind this. And so the idea is, as can be very easily seen in this well-crafted and chosen example, the corresponding output is going to indicate how good of a match did we find between the shape, the pattern, in our filter and the original image. So you can see in this case, the overlap that we had with this green region of our original image, that's exactly what the pattern looks like, which is why, based on, we've discussed this before, this is sort of the maximum activation of this filter. Right? There's no way you can get a better or bigger value for this filter when multiplied with any other region. And so that's what this filtering process is trying to do. The output which we are averaging, and sometimes you will also find examples where you don't average, you simply record the sum of all the elements of your sort of filtered image. But in this case, we do average. The output is an indicator, or the magnitude of the output is an indicator of how strong of a match did we find between our filter and the overlap with the original image. And so once we have that, we can actually repeat it and slide this filter on all possible sort of overlaps. And so convolution is exactly that process. Convolution is the process of taking a filter or a feature, overlapping it with your image, sliding it across, and the way you slide it also matters, which we'll get into in just a second. But at each overlap, you do this element-wise pixel multiplication, you take the sum and you divide it by the number of pixels, which is 9 in our toy example. And so what is shown on the right is what image you would get as the output of this entire process, where we have taken this filter, ran it over the entire image, and so the output is sometimes called a filtered image. So at this point, one of the questions that you generally encounter and think of is the following, that in this example, I have been saying that you would begin on the top left and then slide over all possible values. And if you are just sliding 1 pixel at a time, then you will get what is the output shown on the right hand side. But it is possible to skip a few pixels when you move this filter over to do this convolution process. Also, it might happen that your original image is not a square matrix, right? It's actually the width and the height are different. So there can be a situation where when you were moving this filter over, there is no clean overlap around the edges of the image. And so what do you do in that case is another sort of a question that you may be wondering about. So let's look at that problem. There has to be a relationship between the size of the image, the size of the filter, and the size of the output. So let's look at that example. So shown here is again a 7 by 7 image. And here we don't care about the actual pixel values in this image. What I'm just depicting is what the image size is compared to the filter size. So we have a 7 by 7 image and a 3 by 3 filter shown in green. And so the previous example, I said, you have to cover all the pixels, and so you have to slide it over. So that process would look something like this, that, this is your first convolution calculation where you multiply, take the sum, and store the output. And then you move once over to the right in this case. You repeat that process again. You move a second time. You repeat that process again. You move a fourth time. And by the time you have moved fifth time in this direction, you have covered all pixels in the, along the width of this image. And since you are moving one pixel at a time, the next instance would be you would start from here, because you started with moving one pixel on the right, and so it makes sense to move one pixel on the bottom as well. So if you repeat this, it's not that hard to see that the output image, that the filtered image as a result of this operation would be 5 by 5. Why is it 5 by 5? Very quickly, because we had to do this convolution 5 times, right? So here's one, or this is the second time, and the third, the fourth, and the fifth time to cover the entire image. So since we were moving only one pixel over at a time, this could be parameterized. So you could have a different variation of this where you can move 2 pixels at a time. And so the amount of pixels that you skip when you move your filter over your original image, that parameter has a special name, and that's called the stride of the filter, right? So here's another example, which is exactly the same as before. The only difference is this is a filter applied with a stride 2, which means that after we are done convolving our filter with this top left part of the original image, we will now move 2 pixels over and not 3, or not, sorry, 1 as before. So, you had a previous convolution operation, you move 2 pixels over, you have this region, you can again move 2 pixels over, and now there's no more room to move any further, and so resulting output image size is 3 by 3. So what I want you to think about is that if we have this image and a 3 by 3 filter, what would be the size of the output image if you choose a stride of 3? So, in your head, just try to visualize how many times do you have to move before you can cover sort of all columns in this example with the given 3 by 3 filter. So if you thought about this or visualize this, you would have run into a problem. And that problem is that with the stride of 3, that means that in the next instance, this entire filter covers these 9 pixels. But then we can't take a stride of 3 again, because this last column is left out. So indeed, we cannot apply a 3 by 3 filter on the 7 by 7 image with a stride of 3. Right? So these numbers can't be just arbitrary. There has to be a relationship between the size of your image, the size of your filter, and the stride. And so for a generic image, which is again assumed to be a square image of size n by n, and if you had a filter of size f by f, and you had some value of stride, you can calculate what would be the size of the output image with this relationship which is shown, right? So the output image is always n minus f divided by stride, and add an additional unit to the outcome of that calculation. So for our examples, we have seen n is 7, f is 3, so n minus f is 4. And for the original instance, when stride was 1, we just have 4 plus 1, so the output was 5 by 5. When stride was 2, we have sort of 2 plus 1, so the output was 3. And here you can actually numerically see why 3 doesn't work, because it doesn't add up to any integer number. An integer number means that you have a clean overlap with all images without sort of going out of bounds. But what about that problem that we just encountered? What if I insisted on using stride 3 for this example? Or, I want to solve this problem in general where it may be possible that there is no room for my filter to move as that would result in some of the pixels of the filter becoming out of bounds or extending further than the dimension n. So to solve that, we introduce another trick or another parameter called ZeroPadding. Padding or ZeroPadding is a very clever idea, where the idea is that in order to maintain some clean overlap or account for an integral number of movements of my filter across the image, I will sometimes add a border around my entire image, which is called symmetric padding. And usually we use values of pixels to be 0 in that additional border that we introduce. Hence the name ZeroPadding or ZeroPad the border. Why 0? Because remember that the convolution process involves a pixel-wise multiplication operation. So if you have zeros, it doesn't really affect the output because it's not influencing the output because it's not contributing to the sum of the output pixels. So it's not interfering with this original intuition of whether a pattern exists in this image. It's only sort of a geometric solution to solve this problem that we want a very clean sweep of our filter across our input image. So as is shown here, now in this example, we have a 3x3 filter and we want to apply it with a stride of 1. So we'll just move 1 pixel over and 1 pixel under. And I've also introduced an additional ZeroPadding with a size of 1 as well. So the question we are trying to ask is, what is the output? Where this relationship will help you in figuring out what the output is. So if you figured it out correctly, in this case, our input was 7x7. We applied a 1 pixel ZeroPadding with a 3x3 filter and a stride of 1. The output will also be 7x7. So why? Because actually, by applying the ZeroPadding, we have sort of virtually made our image 9x9 because you have a 0 column here and a 0 column here, and the original image was 7 pixels long. So n is now 9. What is f? F is still 3. So n minus f is 6. Stride is 1, so the denominator is 1, and so we add 1 to the output. So 6 plus 1 is 7, and it's consistent with our relationship as well. In fact, in general, it is very common and usual that when you want to do the convolution layer or operation, you usually stick to a stride of 1. It's very common. And why? Because there is no really good reason to skip any pixels or not visit all the pixels kind of equally often, if you will, because why would you, right? You want to actually figure out where is the overlap between your filter and the image, and so it makes sense to just move over by sort of one step at a time. The only downside is that it's a large number of steps, and if your image is very large, then it could take a long time. In which case you can explore a slightly different stride, but you don't really do that. What you can do if your image is very large is you can have a larger filter. So instead of 3x3, you can have a 5x5 or a 7x7. So you cover a larger portion of the image for every convolution operation. And so what is also shown is that if you have filters of size f by f, and then if you have a padding layer of size f minus 1 by 2, that will preserve this. It will work out so that the filter doesn't overlap anymore outside of the image, other than overlapping with the ZeroPadding layer. So here's an animation which is showing that all of this previous story also works in multiple dimensions, right? So what do I mean by that? I said in our original cross and zero example, I said our images are 2D bitmaps, but true color images have 3 channels: red, green, and blue. But that's not a problem because our convolution will still work. You can have a different filter for each of the respective channels, and that's what was sort of shown here in this animation, where you have the RGB channels of your original image, and for each of them you have a filter, but the process is still the same. You are taking an element-wise product of each of the channels. You are adding a bias term to the output, and then you are storing the result. So let's actually walk through this to make sure that you understand this process. So let's look at our filter. This is the values of the pixel in our filter. We haven't yet explained where this is coming from, but this is just given to us. And so what is this element-wise product? The top row is 0. Here you'll get a -2, and from the bottom row you will also get a 0. So the sum of pixels for this operation would be just -2. Let's look at the middle one, or the middle channel. Again, the top row will give you a 0 element-wise. You'll get -2 again, and you will get a -1 as well with this bottom right. So you have -2 from here, and you'll have -3 from here. And then let's look at this image where you have all zeros. Here you'll get a +2 and then a -1. So you have 1, and then 1 + 2, 3 again. So you have, I think you had a -2, -3, and 3 again. So the sum of the pixels is going to be -2. You add a 1 to that, you will get -1, and that's what we are storing here. Right, so we are doing this convolution on each channel, and in this case, we are not taking the division by the number of pixels. We are merely storing the sum of the convolved process. So to summarize convolution layers, they can accept an image of size width by height by more than one channel or dimension. And then the things that you have to specify for convolution to work is you have to specify the number of filters. So how many filters do you want? For each of the filter that you have chosen, you have to specify the size, f by f, and 3, 5, 7 are good choices. And then you have to specify stride and ZeroPadding. And usually the number of filters k are specified in powers of 2, right? So this is sort of from experience and what usually works and is manageable as well. So you can have like 16, 32, so on and so forth, number of filters. But each one of them can be a different size, f by f. So to go back to our example, this is what the entire convolution is trying to do. It takes the original image and convolves it with a filter to produce this filtered output image. And if you stare at this operation and look at the output, what have we really achieved? So as you can see, our filter has the pattern of what you can call, let's say, a backward diagonal. Okay, so in the 3 by 3 filter, this is the prominent diagonal. And if you look at the filtered output and look at where the high values of the output of the convolution are belonging to, it is the same backward diagonal in this image, which makes sense because in our original input, this is where this backward diagonal exists. And therefore, it makes sense that in our filtered image, those are the pixels where you will have the ones and the higher values as a result of the convolution process. So what I was saying earlier is that you don't just do this for one filter, you can repeat it for as many filters as you want. In fact, I've broken sort of the rule or convention that I stated earlier that usually the number of filters are powers of 2, but here in this example we are using 3 filters because the cross is a pretty simple pattern. So in this slide we have 3 exact same images, but since each of them is getting convolved with a different filter, we have 3 different filter maps. So all in all, in convolution, input image becomes a stack of filtered images where the size of the stack is the same as the number of filters multiplied by the output size of one filter with the other, with the image itself, that we have seen how to determine the output. Right? And so this is what is called a convolution layer. That's it. It was that straightforward. It's this element-wise pixel sum with the intuition to see the overlap with our feature or filter. You take the sum of these outputs of the multiplication. Sometimes you divide it by the number of pixels, not always, but you can. And you store the result in this output filtered image that will tell you where in your original image did that feature exist. But it does, increase the dimensionality of the problem. We did start with just one input image, and based on the number of filters, we are already 3 times, the size of our input image, or close to that, if the output is the same dimension. So if we keep repeating this convolution process, we are going to explode the number of pixels that we have to eventually deal with to classify stuff. So we need another operation as part of this convolution neural network that will actually reduce the size of the output image. And so let's look at that. That process is called pooling, or sometimes you will hear the term max pooling. So pooling is the following idea. Similar to sort of convolution, you specify a window size, and I call it a window and not a filter because a filter has its own values. Here you are just picking a window size. You don't have to populate that window with any pixel values. So you pick a window size, you pick a stride, we know what that means, and then you just slide across the window on the input of the pooling layer. And as you are sliding it across, for every overlap with the input image, you simply record or specify from each window the maximum value. Right? So let's look at an example. So we have our input image, which in this case looks like it's the output of a convolution. So this is a filtered image. And so we have a 2 by 2 window size. And all what pooling is doing is it is looking at the values of the pixel inside the window and simply recording the maximum value. And that's the output. And so you can repeat it for the value of stride, and you will end up with something like this. And since we are logging the maximum value in each window, that's why this operation is often called max pooling. And there are variations of this as well. You don't always have to do max pooling. You can do average pooling or some other algorithm which takes some combination of the pixels in the window. So what pooling has done is that it has reduced the dimensions of the output, because we are actually dropping information, right? So this output doesn't have this information of the 0.77 and the negative 0.11. However, again, if you look at the output image, you see that the spatial sort of pattern is still preserved, right? So even in the output, the backward diagonal has the largest values, which was the property of the input. So pooling is not really, messing up the spatial information. It is preserving that, but it is throwing away some information. So that's one idea why we need pooling, to kind of reduce the dimensionality of the pixels that we want to deal with. Another reason why you would need pooling is because pooling is actually making this whole process somewhat robust and spatially invariant. So what do I mean by that? What I mean by that is we've seen that all crosses are not these ideal crosses in our example. So these negative ones don't have to align so cleanly. They could be a little bit spread out based on the length of the arm of the cross or whether it's rotated and so on and so forth. But pooling takes care of that. Pooling says, I don't really care exactly where you had a big match, but I want to know whether you had a big match with the filter in the vicinity of some region in this image. So it's making us agnostic to where exactly the filter appears, and therefore even if the filtered image appears in some rotated / scaled manner, pooling can capture that to some extent. Okay, and so max pooling is the following idea that, here's another example. You have a input image and you have a pooling window of 2 by 2 and a stride of 2. This is what the output would look like. So just like before, you can accept an input of any dimensions and width by height. It doesn't have to be a square image. And then what you have to specify is the size of the window, which is denoted by F, but it is not really a filter, so keep that in mind. And you have to specify the stride. Right, so you apply pooling to any of the inputs, you get just a reduced version of that input if you are applying max pooling. So as a result of the pooling operation, a stack of images becomes a stack of images of smaller size. So far we've seen, two operations, one which is convolution. I hope the intuition for that is clear, and the other which is pooling, which is actually a much simpler operation than convolution. But if we think back to our previous lecture where we wanted this idea that we need some non-linearity or some activation in a neural network in order to model or capture complicated patterns or nonlinear patterns. Right, so far this process doesn't really explicitly is passing our data through any nonlinear activation layers. So what is the equivalent of like an activation neuron in a convolution neural network? That operation is actually very straightforward. So here's one idea. You can have an entire layer of our previously known rectified linear units or ReLUs. And so here you apply the ReLU operation to the input image in a pixel-wise manner. So what that means is that you look at the value of the pixel. If it's positive, you preserve the value. However, whenever the value is negative, you just record a 0 because that's the ReLU function. And so you can repeat it for all the pixels in your image, and that would be the equivalent of passing your data through a nonlinear activation function. And if you do that enough times, we have seen what it results in is that your receptive fields of the neurons or the layers become more complicated. So they become more capable of identifying complicated patterns, which are much more complicated than these simple diagonal or crosses. So the ReLU is perhaps the most straightforward operation so far that we've seen today, where essentially a stack of images becomes a stack of images with no negative values. So ReLU, again, convince yourself, is not going to interfere with the spatial distribution of where the large values appear in our images, because it's only affecting negative values. Okay, so now no points for guessing what we are going to do next. We have seen this before, that the images which are the inputs of some of these layers, they look a lot like the inputs of other layers and the outputs of other layers as well. So what that allows you to do is you can stack these operations, right? So let's look at this example here. You have your input image as before. You first convolve it with some filter size. Let's say you use 3 filters as we've been looking at so far. You will get a stack of 3 filtered images. You ReLU them first, so you set the negative pixels to 0. Then you do max pooling, and you will get a stack of 3 images with smaller size than what you began with. And now there's nothing stopping you to repeat this entire convolution, ReLU, and pooling operation again with this output as the input. So you can do deep stacking, and this is where sort of the deep convolution neural networks really come from. Right, so you can do this many, many times. You can do convolution, ReLU, pooling. So here, we are stacking them in different order, not the same time every time. And so what you have essentially done is you have taken a complex high-dimensional input image. You have passed it through several convolution and ReLU layers. you have pooled it more than once, and this is the output. Right? So the output is actually, in this example, 3 images which are just 2 by 2 pixels. So we've actually seen this before. This is very similar to what we saw in our previous lecture, where we saw this problem that your input image was a 2 by 2 pixel pattern, and you can build a fully connected neural network and have some output neurons to classify what the pattern is in your simple 2 by 2 image. So if I look at the output of my convolution, ReLU, and pooling layers from before, they look a lot like the pixel values of these simple 2 by 2 images that we know how to already classify. So just to simplify things, I'm going to just denote that entire story of fitting, bunch of neurons and having different edges to tune the weights of that neural network simply by this picture over here that you have your input neurons, which are the outputs of your convolution layer, and then you are just learning a network or essentially a set of weights, so that when you get a image for which you don't know the label, the set of weights is going to give you some kind of score that will indicate what the network thinks is the correct classification of that image. So we've already covered this in the previous lecture, which is why I'm kind of going over it a little bit fast. In fact, what we have seen is, you can have this fully connected layer where essentially you're taking raw pixel values, and through several neurons, you are getting to the output neurons where you output some score of what the network thinks is the chances of whether this image contains a cross or a circle. And we've also seen that you can have more than one of these layers, right? So we've seen this before, that your fully connected layers can also be deep themselves. And at the end of this operation, you will get a score for X and a score for the circle. So while we can stop here and just say that, just look at the raw scores and figure out what the prediction of the network is, usually you can do something even better. So here's another idea, which is called Softmax. And what this idea is, you have the scores or the output scores from the fully connected layers, the output layer of the fully connected neural network. You pass it through this Softmax function, which is essentially normalizing each of these input streams or outputs. So it is normalizing each one of them, but it's doing that in using this exponential function itself, and the output is a probability or a likelihood now. So simply put, these numbers don't add up to 1. So over here you can see that 2 and 1 seem to be very close together than 1 and 0.1. So so you would simply, by comparing the numerical value, you will say that your output of the neural network is the one label which has the score of 2, but you want to actually interpret these scores, which are called logit score. So logit is nothing but terminology to say that these scores are at the output of a neural network. That's what the logit layer is. And so what Softmax is doing is it's taking these values, running them through the Softmax function, where it's for each one of them you calculate e to the power the value of the score divided by the sum of e to the power the value of each of the scores. And the result is that you can interpret these scores as probabilities which always add up to 1. Okay, so Softmax turns these logits into probabilities which sum to 1. And so then you can be more sure that the output that you are using as the prediction is indeed the one which had the highest probability. So the question arises though that why did we do this, right? So if we wanted probabilities, why didn't we simply calculate the sum of the outputs and then compute the probability as the proportion of the magnitude of each of the outputs divided by the sum itself? Why do we have to go through this exponentiation and this complicated Softmax function? So I want you to think about that. So one idea that you would want to go with exponentiation is that why is it better than a sum? Because e to the power a number is kind of, penalizing or adding more weights to higher numbers than smaller numbers, right? So the exponent is a nonlinear function, and so the e to the power something is on the exponential curve. So if your original logit score is high, then e to the power that high number would be even a bigger number. Whereas if your logit score is, let's say, low, then e to the power that number is not going to be proportionally scaled. Right? So you are kind of giving more weightage to higher scores. So you can think of it as that. But that's not the only reason. A more simpler reason, in fact, is that we cannot always guarantee that the logit scores will not have any negative numbers. So when you simply take the sum of that, it will not help you normalize, because one of these logit scores could be a negative number. Another reason is, if you want to solve that problem, you could say, okay, then why don't we take, the absolute value if you want to get rid of this negative problem? And the answer there is, you will see in a bit that sometimes the softmax is not your last layer. You even have another layer after that. Or even if it is the last layer, the error has to back propagate through the softmax layer as well. And so that whatever function you are using to convert the inputs of the softmax into the outputs, it has to be compatible with the back propagation algorithm. And so exponents and log functions are smooth and very easily differentiable. So that's another reason why we add a softmax layer. So all in all, if you put all of what we have seen so far together, this is my example of a deep convolution neural network. Right? You began with a complicated pattern, not so complicated in this toy example, but it could have been. We stack convolution, ReLU, and pooling layers together, have fully connected layers. You have more than one in many cases, followed by softmax, which gives you the probability of whether your input image contained a cross or a circle pattern. And that's all there is to a convolution neural network. So the biggest question that we have very conveniently hand-waved over so far is, where was the oracle, or who gave me these very well conveniently chosen features or filters that overlap with my cross to begin with? Well, one can say for a simple classification task such as cross and circles, even a human can come up with a very reasonable set of what features to look for. But when you are finding vehicles in a video, or pedestrians or cyclists, it's very hard for humans to describe what are the canonical set of features which make up a pedestrian and a vehicle or a cyclist. And so the whole idea and the whole point to using convolution neural networks is that you don't have to specify all of these things manually. The features themselves can be learned using backpropagation. Right? So you only have to specify the size of the filter. Right? That's not something you can learn. So you still have to say whether it's a 3x3 or 5x5. You also have to specify the number of filters, the stride and the padding. All those things are hyperparameters that you will still specify, but you don't have to specify the actual pixel values of the features. You just have to provide an initial value, and then through backpropagation, we will look at the error at the final layer, and then that error will be backpropagated to each of the weights, which in this case would be pixels of your filters or features. And then you would adjust the value of the pixel of the filter appropriately to minimize the error. All right, so we've seen how backpropagation works in a regular neural network. Later, we will see how that works for a convolution neural network. I want to show you an example of how this is actually done in practice. So this is a convolution neural network called AlexNet. this was one of the first CNNs which really made an order of magnitude improvement on image classification task called ImageNet a few years ago. And so here we are showing the complete dissection of this neural network and each of the layers, their ordering, their input, the size of the filters, the number of filters, stride, padding, everything is listed here. And so the reason I have shown this is because in one of the subsequent lectures we will take a closer look at how AlexNet works. Okay, so what about all these hyperparameters, right? Someone has to specify how many features to use, what is the size f by f of each of those filters, what is the stride. I think ZeroPadding is more or less easier to specify given the stride, the image size, and the filter size. And the same goes for pooling layers. That has its own hyperparameters. For fully connected layers, you have to specify how many layers, what are the initial weights, what are the biases. So just like a regular machine learning model, we can tune these each one of these hyperparameters using some validation set and looking at the performance or accuracy of our model on some validation sets for different choices of each of the hyperparameters. But what I want to do in the remaining time today is I want to very quickly go over some best practices or some high-level sort of ideas of how do you deal with these hyperparameters and the weights of the network. All right, so let's talk about activation functions first. So the two functions you have seen so far are sigmoid, and I've sort of also described what inverse what tanh is, and then we have seen ReLU as well, right? So ReLU is the one that we even saw today, where for an input which is less than or equal to 0, the output is 0, and for any positive input, the output is the same value. So it has a constant slope of 1. But you also have some variations of ReLUs called a leaky ReLU, where you don't kill anything which is less than 0 and set it to 0. You let it pass through the activation, but with 1/10 of its magnitude. So you have a very small slope. And then a variation of a leaky ReLU is this exponential ReLU, which is a much more smoother function, which does the same thing as the leaky ReLU. So why do we need so many activation functions, or what is one doing better than the other? So let's start with the sigmoid function, right? So sigmoid is the first function that we encountered, which squashed the inputs to a range between 0 and 1 or -1 and 1 based on how you set it up. And so they are very popular historically because they have a very nice interpretation. But the problem with sigmoid is that it can sometimes kill the gradients during the back propagation, right? So let me tell you a little bit about what I mean by that. So we have seen that the derivative of this function sigma of x is sigma of x times 1 minus sigma of x, right? So we saw that in the previous lecture. So, and we've also seen that during back propagation, you have to multiply the error at the output with the derivative of the sigmoid to get the error at the input of the neuron. Now the problem arises that if the value of x for which you are taking the derivative, if it's a very large positive or a large negative value, then what is the slope of this function near the tails? It's 0, right? So the gradient of a sigmoid when x is large, whether positive or negative, is 0. And in the vicinity of 0 itself, when your x is very small, the slope is again 0. Why? Because the slope is sigma of x into 1 minus sigma of x. And what will sigma of x be when you are close to 0? That value will always be close to 0 as well, or it will be very small. So that's why sometimes during back propagation, a sigmoid function will lead to what is called a vanishing gradient. So that's what the point number 1 is. They kill the gradients. But ReLUs don't suffer with this, okay? Because only when your x is negative are we not using the ReLU. But when your x is large, it actually means that the gradient and the error will be back propagated with equally large amount of weight from the ReLU activation. So that could possibly mean that your adjustment in the weight would be proportional to the the value of x for the ReLU. Also, they are much simpler than a sigmoid because you're not taking exponents of a function. But they do have one problem where if x was negative, then the gradient says that the slope is 0. So you cannot use that information at all. So this is the motivation to explore what is called the leaky ReLU, where you say that when your x is negative, you still output some value and not a 0 value. So that's what it means that the gradient will not die. But this function now is not differentiable. There is this cusp, at this point x equals 0, and so to fix that, you have what is called I don't have an image here. What is called the exponential ReLU, for which we had an image earlier on. By the way, what I'm trying to say here is that one can say, well, this 0.01 is kind of the leakiness factor of this ReLU, but why 0.01 and why not something else? So what another version of the leaky ReLU is that you actually can specify that let me take a max of x or alpha times x, and this value alpha will be learned through backpropagation. So not only are you adjusting the weights of your neural network, so ReLU by convention doesn't have a weight that has to be adjusted because it's a deterministic function. It doesn't have any parameters. But you can parameterize the ReLU by saying that the backpropagation will also tune the value of alpha that yields the best result in minimization of the loss. So in practice, for convolution, especially for images, we use ReLUs. Sometimes we also try variations of ReLUs, but we rarely use sigmoids because of the vanishing gradients. Okay. All right. So that was activation functions. Another question that we kind of stumbled upon is how do you initialize the weights of the network, right? So for a regular fully connected neural network, as well as in the convolution case, the weights are the filters, right? The values of the pixels of the filters are also weights. So how do you initialize them? So to answer that, let's first answer this. Let's say you have a regular neural network, not even a convolution neural network. So what will happen if the weights of that network was 0 when you started training? Right? So think about how does the initialization of this weight affect both the forward and the backward pass. So you might be thinking that, let's talk about the forward pass, right? If all the weights were 0 to begin with in the very first iteration of the forward pass, then you have the input value of the pixels. They all get multiplied by 0, and then we sum them up, so the sum would be 0. And the activation through ReLU or sigmoid would also be 0, and subsequent sums would also be 0 since all the weights are 0. But you would still have some score, whether it is 0 or some value at the output layer. And if you have some score and the ground truth, you will calculate some error. And now the question is, does 0 weights also mess up the back propagation? And the answer is yeah. Having all weights equal or equal to 0 is essentially saying that your network will not learn anything. Because remember, we saw this example where we have two neurons A and B, and the relationship between them was that B was some weight times A, And so when we had the error at the output B, we could calculate the error at the output at the input A by simply multiplying that with the weight. But if the weight was 0, it will just kill this gradient information. So you will have no updates to your weights. That will happen if all the weights are 0. If all the weights are also same, you can convince yourself that all the updates will also be the same, because essentially you are getting multiplied by the same scalar. So we definitely don't want to use a constant or 0 value. So what is reasonable is we can use some small random number. Right? We can draw it from a Gaussian with 0 mean and very, very tiny standard deviation of say 0.01. So this is useful in practice. In fact, for your homework, you will also explore this. But what we know is that for very, very deep networks, even this is not enough. Because eventually, if your weights are too tiny or even too large, all the activations can become 0 or saturated. So let me tell you what you are seeing in this image, because it may not be clear. These plots denote, or we are plotting the mean weight of the entire layer of one of these neural networks, and this is the standard deviation of the entire layer, and this is telling you how the weights are distributed across the layer as time progresses, or in different iterations of the backprop. And you are seeing that all of them are just 0 essentially for a deep network. So people have proposed other ways to initialize the weights which solve this gradients dying out problem. And the point of showing you this is to tell you that this is an active area of research. Right? There's no sort of a rule of thumb that will work forever, but we know enough to try some good initial guesses. So once you have initialized the weights, how do you adjust them? The single word answer is backpropagation. But I want to talk about a slightly different context of how to tune the weights. So how do you know when to stop your learning? Let's put it that way. So let's look at that very quickly. So in general, you will have some training data and some testing data. And then you'll have a network. Let's say this is the network AlexNet, which was trying to identify some classes from ImageNet database. So it might be the case that you predict with 100% accuracy on your training data, and then you pass it some images that the network has never seen before, and you predict all of them incorrectly. And so for those of you who have taken machine learning before, this problem is one of overfitting. Your model has actually just memorized, in some sense, all of your training data. What we want the CNN to do is to learn the filters which describe the generic patterns which make up a car or a penguin on a tree. And if it is failing to do so because when we try to feed it some unknown or unseen images, it is unable to produce or match those filters that it has learned with these new images. So this is a big indication when your training accuracy is super high and your testing accuracy is garbage. That means that your model has overfitted. And so the way to fix it is that you actually look at your training data and you further partition your training data into validation data as well. And so you will withhold some of your training data during the training process and only train on a subset of your training data. So that would look something like this, where we are training the network on a subset of our training data, and we observe the accuracy of the network, and we can then use this network and look at the prediction accuracy on the validation data set this time. So the validation data set is part of the training. It's just that we have kept it away from the network. And so you will get some output value of the accuracy or the loss as compared on the validation set. So then you tune your network And you can again, after every iteration, you can start plotting the validation loss and see how well you are doing on the validation data set. And the loss will hopefully decrease if you are doing learning, and at some point it will start to increase, and that's when you know when to stop. Right? So you should stop because this is when you are overfitting. Why do you know that this is overfitting? Because validation was kind of behaving like a test set for your training process. So why do we have this validation, or where do we get this validation data set? You can actually swap the validation data sets and do this process again. So the next time around, you have a different part of your training which is validation, and you can repeat the entire thing again. And this will tell you how to tune when to stop training and to prevent the overfitting. So even in your homework, you will see I'm going to ask you to monitor the loss function and monitor the validation loss to tell you, or think about when your model is not learning properly and when is it overfitting. So another kind of good indication that something is wrong is if your loss function looks like this over time, this is an indication that your model is not well initialized, because the loss didn't decrease to begin with, and then something happened, it came out of a local minimum. All right, so while we are on the topic of loss, I want to just introduce a couple of more terminologies that you will see next week. So recall, and we've seen this in depth during our first module of parameter estimation and nonlinear optimization. So I'll be fairly quick to just recall some of the key concepts and introduce the new terms. But we know that estimating parameters and the loss is in general a nonlinear function. So in sort of 3D plot of loss versus the values of the weights on the x and y and the value of the loss on the z, that could be a function like this. And what we want is not to get trapped in any of these local minimas, but the true minima looks to be somewhere here near this purple region. And so we have seen that gradient descent or stochastic gradient descent, it starts with an initial guess and it computes the direction of the steepest gradient, and then it moves towards that direction to eventually get to the minima of this function. And one of the things that we've also discussed is once you have identified which direction to move in, there is still a question of how much of a step do you take in that direction, right? So, and we saw that there's like a Newton's method and Gauss-Newton method to figure that out. Some complicated functions also take care of the second derivative to figure this out. But in the very simplest form, you have to choose whether you are taking a step which is the same as the magnitude of the gradient, or a larger step, or a slightly smaller step. But if your steps are too small, then your learning rate is what is the correct term, is too small, then it will take a long time for you to learn or get to this global minimum. And that's a problem. And on the contrary, if your learning rate or the step is too large, then you will just oscillate about the global minimum and never actually get close to it. So one new idea that we haven't seen is the following. Let's say you had a learning rate of 0.01 or some value, and you had the direction of the steepest gradient. And so you want to start from this gray dot is your initial guess. This is your steepest gradient. And so you start making small steps with increments of the learning rate and the gradient direction. And then you reach the point where now you have a new steepest gradient. But here is the idea called momentum, which actually is very similar to this idea of Levenberg-Marquardt algorithms that we saw in the first module, if you recall those. But the idea is that instead of now switching my direction of how to adjust the weights, I'm not going to just simply follow the steepest gradient anymore, but I'm going to follow something which is close to the steepest gradient. And how close it is to the steepest gradient compared to my original direction of steepest descent is governed by some parameter called momentum, which is a number between 0 and 1. So when momentum is large, you continue close to what you were already continuing on, which is also the physical interpretation of momentum, that you carry that inertia with you. But if momentum is small, you diverge to match the direction of the new gradient. So tuning this momentum along with the learning rate are also things that you can change to change how fast your network learns. Okay, so in simply put, the actual step is some convex combination of the gradient and the velocity or the momentum direction. So mathematically, you recall in gradient descent, we had the update to the weight is the previous value times some learning rate and the gradient itself. And in momentum, the update is the previous value with the learning rate and velocity, where velocity is some momentum times the previous velocity and the new gradient. Okay, so we've seen what a CNN is, how it works. We briefly discussed activation functions, weight initialization, and some properties of the optimization algorithm that actually tunes the weights. And so the last thing I want to discuss today is a high-level idea of how actually the training process works when your data is large. Right, so let's take a look at this example where you have a large data set of images of different kinds of vehicles, and you want to train a network to identify the correct category of the vehicle from the image. Right, this you can imagine is very relevant to our autonomous vehicles. So you spend time deciding the architecture. You may look at existing neural networks which solve similar problems to motivate which layers to use, how to stack them, so on and so forth. And then the question becomes, how do you train it for such a large data set? And this is a more practical problem now. So let's say you have 50,000 images in your data set. So this data set might be too large to fit in the memory at the same time. Right? It may be like hundreds of gigabytes or terabytes worth of data. A better way is to divide the data into something called batches. And so the way to do that is, let's say you have 50,000 samples. You specify a parameter called batch size of 2,500 samples in this example. So that would mean we have 20 batches to cover the entire data. And then you train your network one batch at a time, essentially. So for each batch, which has 2,500 samples, I will first do the forward pass for all images in my batch. So remember, I am not doing a forward pass and back propagating for every single image at a time. But instead, I look at the entire batch, I pass all of them, and then I'll get a loss for the entire batch. And then I will do one iteration of back propagation to adjust the weights for this batch, which contains many, many samples, 2,500 to be precise. And so this forward and backward pass on one batch is what is called an iteration. So what is one batch again? It's the number of samples that have gone through the network before I do backpropagation or before updating the weights of the network or the parameters of the network. So this is for a single batch. When I repeat it and I have gone through all of the batches, that is called one epoch. So one epoch is nothing but a term to describe that your network has seen all 50,000 images or all the data once, which means that you have done the forward and backward pass on each of the batches at least once. And that's the definition of an epoch. So if you had 50,000 samples, batch size of 2,500, one epoch will give you 20 opportunities to update the weights or the parameters of the network. Why 20? Because you are dealing with 2,500 images at a time when you do the forward pass, and it's during the backward pass or during the backward iteration when you actually do the parameter update. So this is how you deal with practical issues such as not all data will fit in the memory at the same time, so you divide it into batches by specifying some batch size. And the other thing is you don't just train the entire network once, you train it for multiple epochs. So if I want my data to be seen and to be used for tuning at least 10 times, I will train my entire network for 10 epochs, and in each epoch there were 20 opportunities to adjust the weight. So overall, during my entire training, I am giving it 200 opportunities to tune the weights. So these terms, epochs, batches, and iterations appear often in literature and books, and so I wanted you to know what they mean. All right, so to wrap up, excuse me. To wrap up, CNNs are not just for images. What is an image? An image is nothing but input data where for a given sample, it is closely spatially related to other samples in its vicinity, or for a given row or column of our image, the pattern or what an object is depends upon adjacent rows and columns. In fact, you can even specify audio data as an image, where the number of columns is, say, some window of time, and the rows is the intensity of the sound signal in some frequency domain. And once again, due to the nature of this data set, things which are related closely in time are some feature or pattern, and so are things which are related closely in frequency. Or let's look at text data from the domain of natural language processing. I can create a very sparse image, but nonetheless an image where there is a relationship between the rows because they are organized as how English words appear in the dictionary, in what order. And the columns of my image indicate where in the sentence does a particular word appear. And again, this order is not interchangeable, right? So this pattern depends or captures or is very specific to this image that you see. So CNNs can capture these patterns and data. If your problem can be made to look like finding crosses and circles in an image, then you can use CNN. If you cannot do that, then they are not that useful. So for example, let's look at this data set. This data is what you can call customer data. So when you visit a website or do some shopping online, if someone is tracking your activity, this is their data. That's what it may look like. So the columns of this data are the name, the age, some email ID, address, other attributes, IP address, whatnot of an individual, and the rows are just different individuals. But you can interchange the rows because they are kind of independent from each other, right? Person A is not related to person C or E, or at least that's not how we are modeling it. And likewise, you can change the columns of this data with each other, the ordering of the columns, and it would still make the same amount of sense. Because once again, the IP address has nothing to do with age. It's a completely different attribute. So it's not related in time, it's not related in space. So if the data is just as useful when you swap out your columns and rows, or in other words, the columns or the rows are linearly independent, then CNNs are very less useful because there was no coherent pattern to begin with that they could have captured, because your pattern could have been anything and it would have still made sense in the terms of the data set. So we are great at finding patterns and classifying them as crosses and zeros. In fact, that's what's going to be your first convolution neural network that you will make next week. So I'll stop here, and next week we will look at all of what we have learned in terms of processing images using neural networks, and today we talked about convolution neural networks on large data sets. So starting next week onwards, we will really look at some very specific examples of how this works for the problem of self-driving, and you will also do your first homework assignment for this module where you will train a neural network, in particular a CNN neural network for the crosses and circles problem that you saw today. Okay, so I'll stop here and then resume next week.